Very good morning to Dr. Nazin Shah. My name is Nawanida Analaki Toyoraj. My matrix ID is 211291020. And today we're going to look at Lab 5, which is the effect of different PID value. So in this experiment, the objective of this lab is to able to use MATLAB commands for PID analysis to analyze the effect of different value P, I, and D in a control system. So moving on to the first part of this experiment, we are going to look at this is the figure 2, figure 3, and this is the answer part for procedure 3.1.1. Okay, as for this is without PID controller. So basically the numerator is 1, the denominator is 1, 3 and 1, and as usual the GP is TF, numerator and denominator, and for system feedback is GP and H. So this response is response to TF without PID controller. So the second one is with PID controller when Kp is increased while Ki and Kd is constant. So the numerators as usual the 1, 1, 3, 1 this is the same, but however we are inputting the Kp value, Ki value and Kd value. So here we input 10, 1 and 1. So here we input 15, 1 and 1. So this is the graph for the response to a TF when Kp is increased while Ki and Kd is constant. And this is when Ki is increased while Kp and Kd is constant. So the numerator and denominator are the same. The H is 1, the Kp1 is 15, Ki is 3, Kd is 5, the Kp2 is 15, Ki2 is 7, and Kd2 is 5. So this response is for TF when Ki is increased while Kp and Kd are constant. So basically the next one is when Kd is increased while Kp and Ki is constant. The numerator denominator are the same, the GP and everything is same. Kp1 is 15, Ki is 7, the Kd is 3, Kp2 is 15, Ki is 7 and Kd2 is 5. So the same thing, but this is a response to TF when Kd is increased while Kp and Ki are constant. So this is the table. For the table without the PID controller is 2.59, 0 and 4.6 as settling time, and there's no value for steady state error. The overshoot is 0, rise time is 2.59. With the PID controller, when Kp is increased while Ki and Kd is constant, we are using this transfer function, and the value for rise time is 0.595, the overshoot is 3.1, and the settling time is 13.4, the steady state error is 1. So as for a transfer function, with this transfer function, the value is 0.419 as rise time, the overshoot is 11.4, the settling time is 15.2, and the steady state error is 1. So whereby we are going for the second part, when the Ki is increased while Kp and Kd is constant, this is the transfer function, and this is the transfer function. So the rise time is 0.49457, there's no value for overshoot, and the settling time is 2.3, and the steady state error is 1. So the rise time is 0.425 for this transfer function, the overshoot is 1.9, the settling time is 0.678, and the steady state error is 1. So the last function is this 2, when Kd is increased while Kp and Ki is constant. For this transfer function, the rise time is 0.416, the overshoot is 7.2, the settling time is 1.650 and 1. And this is for this transfer function, the rise time is 0.425, the overshoot is 1.9, the settling time is 0.678, and the steady state error is 1. So now I'll demonstrate the functions in the graph using MATLAB. So let's go to MATLAB. So here in MATLAB, we're going to be looking at the first graph, which is without the PID controller. As you can see, this is the coding. So now let's play it. And when we start to play it, let's input the characteristics, the peak response, the settling time, and the rise time, and the steady state. So let's input the values. This make it bigger. So as you can see, the rise time is 2.59 seconds, the settling time is 4.6, the final value is 0.5. So now let's move on to the second graph, which is a response to TF when Kp is increased while Ki and Kd is constant. So now let's run the graph. So as you can see, this is the graph. I'll input the characteristics, peak response, and settling time, and I'll be inputting rise time as well, and steady state. So let's see the values. You can see this is the values. So as you can see, this is for PID2 and this is PID1. This is PID2, system value, the rise time. So this is the graph for response to TF when Kp is increased while Ki and Kd is constant. So now let's move on to the third graph, which is this. And now let's play it, and you can see the response to TF and Ki is increased while Kp and Kd are constant. So I'll input the characteristics again, the settling time, rise time, and the steady state. You can see, so this is the response for PID1, and now let's go for response for PID2. So as you can see, this is the response for PID2, and this is the rise time, settling time, and final value. So now let's go for the last graph, which is this one. When response to TF when KD is increased while KP and KI are constant. So I'll play it. Okay, now let's input the characteristics, peak response, settling time, and the rise time, and steady state. So now let's look at PID1 first. This is PID1. Now let's look at PID2. That's PID2, and this is system. So this is the response to a TF when KD is increased while KP and KI are constant. So this is the calculation. As for the task 4.1, the equation is mx plus bx plus kx equals to f. For s1, Laplace transform ms squared times s plus bs times s plus kx in brackets s is equals to fs. Transfer function xs over fx equals to 1 over ms squared plus bs plus k. S3 is m equals to 1 kg, so b equals to 10 k over SNM, k equals to 20 nm. So for S4 is substitute S3 into transfer function xs over fs, which is 1 s squared plus 10s plus 20. So now let's go for the next one. Without the PID controller, this is the numerator 1, the denominator is 1, 10 and 20, and the GP is as usual. This is response to TF without the PID controller. So this is the 1. And as for P controller, this is the same numerator and denominator, the H, the system feedback, and the KP is 300, KI is 0, and the KD is 0. So this is response to TF when KP equals to 300 while KI equals to 0 and KD equals to 0. So this is the graph, and this is the PI controller. This is the numerator and denominator. So KP is 300 as usual, this is R the same. This is the response to a TF when KP equals to 300 while KI equals to 10 and KD equals to 0. So this is the graph, and this is the PD controller. The Kp is 350, the previous one was 300. This is a response to a TF when Kp equals to 350 while Ki equals to 0 and Kd equals to 50. This is the graph, and this is the PID controller. The numerator are the same, and the Kp is 350, Ki is 300, and the Kd is 50. So this is the response to TF when Kp equals to 350 while Ki equals to 300 and Kd equals to 50. So this is the graph. So I'll show you the table. The rise time is 0.833, the overshoot is none, and the settling time is 1.49, and the steady state error is 0.476. This is for without the PID controller. And with the PID controller, for this transfer function is 0.727, 40.1 as overshoot, and settling time is 0.772, and the steady state error is 0.938. For this transfer function, whereby 300s plus 10, this is the rise time is 0.077, the overshoot is 31.5, the settling time is none, the steady state error is 1. For this transfer function whereby it involves PD controller 50s plus 350, so the rise time is 0.0419, okay, and the overshoot is 2.22 times 10 to the power of negative 14, and the settling time is 0.0758, and the steady state error is 0.946. So as for this transfer function, the rise time is 0.0548, there's no overshoot, and the settling time is 0.831, and the steady state error is 1. So now I'll show you the graph in MATLAB. So this is the graph for without the PID controller. As you can see, the numerator is 1, the denominator is 1, 10, and 20. And as usual, now I'll run it. So this is the characteristics, peak response, okay, the settling time, then the rise time, then the steady state. So I enlarge it. Okay, so this is the settling time, and this is the okay, the rise time is 0.833, the settling time is 1.49, the final value is 0.0476. So now let's go for the second graph. Okay, this is the one which is response to TF and Kp equals to 300 while Ki is 0 and Kd is 0. So you can see Kp is 300, Ki is 0, Kd is 0. So now I'll run the graph. So this is the graph. I'll include the peak response, then the settling time, then the rise time, then the steady state. So now I'll just label it. Okay, so for this, the peak amplitude is 1.31, the overshoot is 40.1, and then it's 0.184 seconds. Then the rise time is 0.0727, the settling time is 0.772, and the final value is 0.938. So as for this, the rise time is 0.833, the settling time is 1.49. This is the response to TF when Kp equals to 300, while Ki is 0 and Kd is equals to 0. So now let's move on to the next graph. So as you can see here, this is when Kp equals to 300, while Ki is 10 and Kd is 0. So now, as you can see here, this is the change here. Now let's run the graph. So I'll label it again, peak response, settling time, then the rise time, then the steady state. So I'll just label it once again. And okay, so the peak amplitude is 1.32, the overshoot is 31.5, and the time is 0.185. So the rise time is 0.077, the final value is 1, the rise time is 0.833, and the settling time is 1.49. So this is the graph for response to TF and Kp equals to 300, while Ki is equals to 10 and Kd equals to 0. Now let's move on to the last graph. which is the response to TF and KP equals to 350 while KI equals to 0 and KD equals to 50. So this is the change here. So now just run the graph. So I'll include the parameters again, the settling time, the rise time, and the steady state. So I'll label it once again. Okay, so here, okay, here. So the rise time is 0.0419, the settling time is 0.0758, the rise time is 0.833, the settling time is 1.49, and the final value is 0.946. So with that, that sums up for the graph, and thank you for listening.